Welcome to the deep dive. Today, we're really getting into solutions and alloys. We've got the slideshow. It was originally made to teach students the basics, but
Hmm.
we're going to go a little deeper with it. Think of it as like a behind-the-scenes look at the stuff that makes up our world.
It really is amazing how often we see this stuff in our daily lives,
Yeah.
but we never really stop to think about the science behind it,
No, right. Like, we all know salt water is different than regular water, but why? And how come steel is strong enough to build skyscrapers with? That's what we're talking about today.
It's making those connections between what we see and the chemistry that makes it all work.
Okay, let's jump in. So the slideshow starts out by defining a solution. A solution is a homogeneous mixture where one substance dissolves into another, like when you stir sugar into your coffee. Seems pretty simple, but there are actually a lot of different kinds of solutions out there.
Yeah, that's because there are so many different things that can be the dissolver and the dissolvee, the solvent and the solute. We're talking everything from salt water and air to even vinegar.
Wait, vinegar is a solution? I just thought it was like
Well,
vinegar.
think about it. Vinegar is acetic acid dissolved in water. So the water is the solvent, the thing doing the dissolving. And the acetic acid is the solute, the thing being dissolved.
Okay, I see. So it's all about one substance being completely mixed into another. And that brings us to alloys. Are alloy solutions too? I mean, they're mixtures, right?
Hmm. That's where things get a little more complicated. Alloys are homogeneous mixtures, but instead of dissolving, they're formed by melting and fusing elements together. And at least one of those elements has to be a metal. Think about steel. Steel is a combination of iron and carbon.
Oh, okay. So it's the process that makes them different. Solutions are about dissolving at a molecular level, and alloys are about melting and fusing the elements. And I guess that different process is why alloys have properties that are so different from the original elements, right? Like steel is way stronger than just plain iron.
Exactly. It all comes down to how the alloy is formed at the atomic level.
Let's get back to solutions for a second. I remember from chemistry class the terms solvent and solute, but it's always good to refresh our memories, right?
Absolutely. So the solvent is the thing that does the dissolving, and the solute is the thing that gets dissolved. Salt water is the easiest example. Water is the solvent. Salt is the solute.
Simple enough. Now, the slideshow mentions aqueous solutions. Is that just a fancy way of saying solutions where the solvent is water?
Exactly. Water is sometimes called the universal solvent because it can dissolve so many different things. And because water is everywhere, aqueous solutions are really important in nature.
It's pretty amazing when you think about it. Salt water, sugar in water, even our blood. It's everywhere.
Exactly. And since water is so important to life, understanding how aqueous solutions work is really important in a lot of areas of science.
Speaking of aqueous solutions, the slideshow talks about something called tonicity. It talked about hypertonic, and isotonic solutions.
Oh yeah, tonicity. To put it simply, it's all about how much solute is in a solution. So imagine you have two solutions side by side. A hypotonic solution has less solute compared to the other solution, and a hypertonic solution has more solute. And an isotonic solution, they have the same amount.
Okay, I get it. The prefixes help. Hypo means less, hyper means more, iso means equal. But how does all this work in the real world?
Well, get this. The slideshow gives this really cool example of red blood cells. If you put a red blood cell in a hypotonic solution, it swells up.
Hold on, the solution can change the shape of a cell. Why does that happen?
It's because water always wants to be balanced. Water will move across the cell membrane to try to make the concentration of solute the same inside and outside the cell.
Hmm.
So in a hypertonic solution where there's less solute outside the cell, water rushes into the cell, and that makes the cell swell up. In a hypertonic solution, the opposite happens. Water moves out of the cell and it shrinks.
Wow, that's incredible. So what happens in an isotonic solution?
That's where things stay balanced. The concentration of solute is the same inside and outside the cell. So there's no movement of water. The cell stays the same.
That makes sense. And that's probably why isotonic solutions are so important in medicine. Like when someone needs IV fluids, you don't want their red blood cells swelling up or shrinking.
Exactly.
Yeah.
Using an isotonic solution like saline solution makes sure the cells stay balanced. It's a great example of how understanding these basic concepts can be really important in the real world.
Okay, so we've covered a lot about solutions. Ready to move on to alloys?
Sure. But before we do, have you ever had a cavity filled at the dentist?
Of course. Who hasn't?
Well, the material they use to fill cavities, dental amalgam, it's actually a solution of mercury and silver. It's kind of a cool example of how metals can be part of solutions, which leads us nicely into talking about alloys.
I see what you mean. It's like a bridge between the two, going from dissolving metals in solutions to combining them in alloys.
Exactly. And with alloys, we're talking about a whole different level of mixing and bonding. Remember, alloys are formed by melting and fusing elements together. And at least one of those elements has to be a metal.
Right. And this melting and fusing process is what gives alloys their unique properties. They're often stronger, harder, or more resistant to corrosion than the individual metals.
Exactly. It's all about how the atoms are arranged when the elements are combined.
Okay, so let's talk about those different types of alloys. The slideshow mentions a bunch: heterogeneous, interstitial, substitutional, and solid solution. Before we get into the specifics, I have to admit I'm still a little fuzzy on the difference between solid solution alloys and substitutional alloys. They both seem to involve swapping out atoms, right?
Yeah, that's a great question. It is easy to get those two confused. They both involve replacing some of the original atoms in a metal with atoms of a different metal. The key difference is how those atoms are arranged in the alloy. Think of it like this. Imagine a 3D chessboard where every square has to be filled by an atom.
Okay, I'm picturing a very organized atomic chessboard.
Right, so in a substitutional alloy, you're basically swapping out some of the pieces on the chessboard for different pieces. But you can put those pieces anywhere as long as they're about the same size as the original piece. The substitution can be random, but in a solid solution alloy, the substitution has to follow a specific pattern.
So it's like the difference between randomly throwing seeds in a field versus planting them in neat rows.
Yeah.
Substitutional alloys are more random, and solid solution alloys are very precise.
Exactly. And that organized structure in solid solution alloys often makes the material even stronger and harder. It's all about how those atoms are arranged.
This reminds me of something we talked about earlier, how the properties of an alloy can be completely different from the metals it's made of. It's amazing how just arranging atoms in different ways can have such a big impact.
It really is. And it's not just about strength and hardness. We can design alloys to have other special properties,
Mhm.
like resistance to corrosion.
Corrosion resistance, you mean like how some metals rust and some don't?
Exactly. Some alloys are designed to resist rusting or breaking down, even in harsh environments. Like stainless steel, it has chromium in it. And the chromium actually forms a protective layer on the surface that prevents corrosion.
So it's like the chromium sacrifices itself to protect the rest of the alloy? That's pretty cool.
It is, and it shows how we can actually change the makeup of an alloy to get the exact properties we want.
This is blowing my mind. Okay, so we've talked about solid solution and substitutional alloys. What about the other types?
Okay, let's start with heterogeneous alloys. Remember our 3D chessboard analogy. In a heterogeneous alloy, the different types of atoms aren't evenly spread out. They kind of clump together. So you'd have groups of one type of atom next to groups of a different type.
So it's not a perfectly even mix like we see in solutions. Are there any common examples of heterogeneous alloys?
There are actually more than you might think. Concrete, granite, even just mixing oil and water. Those are all examples of heterogeneous mixtures.
Okay, that makes sense. Now, what about interstitial alloys? What makes them different?
Interstitial alloys are all about those spaces between the atoms in the crystal lattice. Remember how every square on our 3D chessboard needs to be filled? Well, in interstitial alloys, you have these tiny atoms, usually nonmetals like carbon or nitrogen, that squeeze into the spaces between the bigger metal atoms.
So it's like they're filling in the gaps on the chessboard.
Exactly. And when these little atoms squeeze in, they actually change the shape of the lattice, making it harder for the atoms to move past each other. This is why interstitial alloys are often much stronger and harder than just the pure metal.
It's like those tiny atoms are like little wedges jamming up the works.
That's a great way to think about it. The classic example of an interstitial alloy is steel. Those carbon atoms fitting between the iron atoms are what makes steel so strong.
Ah, so that's how we get those super strong materials that can hold up huge buildings.
Right, and the slideshow mentions another type of alloy called a solid solution alloy. Remember our perfectly organized 3D chessboard. In a solid solution alloy, the substitution of atoms happens in a very specific way.
So it's like there's a blueprint for how the atoms are arranged.
Exactly. And again, this precise substitution often leads to better properties like increased strength and hardness,
Yeah.
and even some unique electrical properties.
Okay, I think I'm starting to get the bigger picture here. The type of alloy, whether it's heterogeneous, interstitial, substitutional, or solid solution, it all comes down to how the atoms are arranged in the material. And that arrangement is what gives the alloy its special properties.
That's a great summary. It's really fascinating how these little changes at the atomic level can make such a big difference in the materials we use every day.
Speaking of everyday materials, can we switch gears and talk about how alloys are actually used? I mean, we know they're in all sorts of things, but can we get a little more specific? What are some real-world examples?
Absolutely. The slideshow does a really good job of showing how alloys are used in different industries, from construction and transportation to electronics and medicine.
Okay, I'm ready for a tour of the alloy world. What are some of the highlights?
Well, let's start with construction. Like we talked about earlier, steel is a really important material in buildings and bridges because it's so strong.
Makes sense. You don't want those materials breaking under pressure.
Right. And then there's transportation. Think about aluminum alloys. They're super light but still strong, which makes them perfect for cars and airplanes.
So it's all about finding the right combination of properties for the job.
Exactly. And the properties of alloys aren't just limited to strength and weight. In electronics, for example, solder, which is used to connect different metal parts, is often an alloy. And gold alloys are used for electrical contacts because they conduct electricity so well.
Wow. So alloys are really important in a lot of different technologies. It's not just about their physical properties. Their electrical properties are important too.
You got it. And we can't forget about the medical field. Titanium alloys are really strong and durable, but they're also biocompatible, meaning they don't cause problems in the human body. This makes them perfect for things like implants and artificial limbs.
It's amazing how we can use alloys to actually help people in such a direct way.
It really is. And of course, we can't forget about jewelry. Pure gold is actually quite soft and easy to damage. So it's often mixed with other metals like silver, copper, or nickel to make it stronger and to give it different colors.
So that's why my gold ring doesn't bend out of shape every time I bump it into something. It's amazing how alloys are literally all around us, from the buildings we live and work in to the jewelry we wear.
It really shows how creative humans are and how we can change materials at such a basic level. By understanding the science of alloys, we've opened up a whole new world of possibilities.
Okay, so we've talked a lot about the different types of alloys and how they're used, but I'm still curious about something. We keep saying that the properties of an alloy are different from the elements that make it up, but how does that actually happen? What's going on with the atoms that creates these new properties?
That's a great question. And to be honest, it's a bit more complicated than we have time to explain right now. It involves things like electron configuration, metallic bonding, and how the arrangement of atoms affects things like strength and flexibility and conductivity.
Ooh, that sounds like a whole other deep dive. So we're leaving our listeners with a bit of a cliffhanger.
I guess so. But I think it's a great opportunity for them to do some more exploring on their own. After all, curiosity is what drives real learning.
I love it. We've given them the foundation. Now it's their turn to go out and build something amazing with it.
Exactly. The world of material science is huge and incredibly fascinating.
So before we wrap up this deep dive into solutions and alloys, what's the main thing you want our listeners to take away from this?
I think the most important thing is to realize that these concepts aren't just abstract ideas. They're all around us, literally shaping the world we live in. From the steel in our skyscrapers to the saline solution they use at the hospital, solutions and alloys are a huge part of our lives.
I totally agree. Understanding the science behind them gives us a whole new appreciation for how ingenious and complex both nature and human innovation can be.
Well said. It's been great exploring this topic with you.
And with our listeners, thanks for joining us on this deep dive into the fascinating world of solutions and alloys. We hope you learned something new and feel inspired to keep exploring.
So, where were we?
Oh, right. We were about to talk about heterogeneous alloys.
Oh, yeah, heterogeneous alloys. So remember that 3D chessboard we were talking about? With heterogeneous alloys, the different types of atoms aren't all spread out evenly. It's more like they clump together. You have little groups of one type of atom next to groups of a different type.
So it's not a perfectly smooth blend like in solutions.
Right.
Are there any like everyday examples of heterogeneous alloys?
Oh, yeah, definitely. Think about things like concrete or granite or even just oil and water mixed together. Those are all heterogeneous mixtures.
Okay, I get it. So what about interstitial alloys?
Interstitial alloys are all about those little gaps in the crystal lattice. Remember how we said every square on the chessboard has to be filled? Well, with interstitial alloys, you have these really small atoms, usually non-metals like carbon or nitrogen, and they can fit into those spaces between the bigger metal atoms.
So it's like they're filling in the gaps on the chessboard.
Exactly. And when those small atoms squeeze in, they actually kind of distort the lattice structure, and that makes it harder for the atoms to slide past each other. That's why interstitial alloys are usually a lot stronger and harder than the pure metal by itself.
It's like those tiny atoms are like little wedges jamming everything up.
That's a great way to think about it. The best example of an interstitial alloy is steel. It's those carbon atoms fitting between the iron atoms that gives steel its strengths.
Oh, wow. So that's how we get those super strong materials that we can use to build huge things.
Yep.
Okay, so we've covered heterogeneous, interstitial, substitutional, and solid solution alloys. I think I'm starting to see the bigger picture here. It seems like the type of alloy really just depends on how the atoms are arranged.
You got it.
And that arrangement is what gives the alloy its unique properties,
Exactly.
either its strength or hardness or resistance to corrosion.
It all comes down to how those atoms are arranged at the microscopic level.
It's amazing how these tiny little changes can have such a huge impact on the materials we use every day.
It really is.
Okay, so we've talked about all these different types of alloys. Can we talk about how they're actually used? I know they're in a lot of different things, but can we get into some specifics?
Sure, the slideshow gives some really good examples of how alloys are used in different industries, like construction, transportation, electronics, even medicine.
Okay, I'm ready for a tour of the world of alloys.
Let's start with construction.
hmm
Like we were saying before, steel is super important for buildings and bridges because it's so strong.
Right, you don't want those things collapsing.
Definitely not. And then there's transportation. Aluminum alloys are really light, but also strong,
hmm
which makes them perfect for cars and airplanes.
So it's all about finding the alloy with the right properties for the job. And it's not just strength and weight either, right?
Right. Think about electronics. Solder, the stuff they use to connect different metal parts, is often an alloy. And they use gold alloys for electrical contacts because they're such good conductors.
Wow. So alloys are really important in technology too.
Oh yeah, they're everywhere.
What about medicine?
Well, titanium alloys are really interesting. They're strong and durable,
hmm
but they're also biocompatible, which means they don't cause problems when they're put in the human body.
So they're safe to use for things like implants and artificial joints.
Exactly.
It's incredible how we can use these materials to help people in such a direct way.
It really is. And of course, we can't forget about jewelry. Pure gold is actually pretty soft and easy to damage, so they mix it with other metals like silver, copper, or nickel to make it stronger and to give it different colors.
Oh, that makes sense. So that's why my gold ring doesn't bend every time I bump it into something.
Exactly.
Wow. Alloys are everywhere.
They really are.
They're in buildings, cars,
Yeah.
airplanes, computers, medical implants, jewelry.
It's pretty amazing.
Okay, so we've talked about all the different types of alloys and how they're used. But I'm still curious about one thing. We keep saying that the properties of an alloy are different from the properties of the elements that make it up. But how does that actually happen? What's going on at the atomic level that gives the alloy these new properties?
That is a great question. And to be honest, it's kind of complicated. We would take a whole other deep dive to really explain it.
Oh man, another cliffhanger.
Well, I think it's a good opportunity for our listeners to do some exploring on their own.
Mm-hmm.
You know, curiosity is what leads to new discoveries.
That's true.
There's a whole world of material science out there just waiting to be explored.
I like that. We've given them the basics. Now it's their turn to go out and discover something new. I love that idea, encouraging people to keep learning and exploring. You know, we've only scratched the surface here. There's so much more out there to discover.
Definitely. Who knows? Maybe one of our listeners will be the one to come up with the next big alloy or discover some amazing new solution.
That would be awesome. Okay, so before we wrap things up completely, I wanted to go back to something we were talking about earlier, tonicity. We talked about how it affects cells, but you mentioned that it's important in other areas too, like agriculture and food preservation. Can you give us a few more examples of how tonicity plays a role in the real world?
Oh, sure. Tonicity is all about how water moves. And that's a really basic process that's important for all kinds of things, like plants. If you see a plant wilting, it's usually because the cells have lost water. To help the plant, you can water it with a hypotonic solution.
So the water would move into the plant cells and make them plump up again.
Exactly. The lower concentration of solute outside the cells pulls the water in, and that rehydrates the plant and helps it stand up straight again.
That's a great example. What about food preservation? You said that hypertonic solutions can be used to keep food from going bad?
Right. Think about things like pickles or jams. They're preserved in solutions that have a lot of salt or sugar. These hypertonic environments actually pull the water out of any bacteria or fungi that might be trying to grow, and that prevents them from spoiling the food.
Oh, wow. So it's like dehydrating the microbes.
Exactly.
It's amazing how something as simple as changing the concentration of solutes can make such a big difference in how long food lasts.
It really is. And it's not just plants and food. Tonicity is also important for how our kidneys work, how our bodies regulate blood pressure, even how we absorb medicine. It's a really important concept.
It sounds like tonicity is kind of a hidden hero in science, quietly working behind the scenes, affecting all sorts of things we might not even realize.
That's a great way to put it.
Yeah.
It just goes to show that even the simplest scientific ideas can have a huge impact on the world.
This has been such an amazing deep dive. We've learned about solutions and alloys, what they are, the different types, and how they're used in so many different areas. I feel like I have a whole new appreciation for the materials that make up our world.
Me too. It's been great to really dig into these concepts and see how something as small as atoms and molecules can affect the things we see and touch every day.
I think that's a perfect way to end this, appreciating how everything is connected, from the simplest solution to the most complex alloy. It's all about understanding the basic building blocks of matter and how they work together to create this incredible world we live in.
I couldn't have said it better myself.
Well, on that note, we're going to wrap up this deep dive. A huge thank you to our expert for being here and sharing your knowledge with us. And thank you to all of our listeners for joining us on this journey of discovery. We hope you learned something new and maybe even got inspired to keep exploring the amazing world of material science. Until next time, stay curious.